So for a long time, you were told you can't square root negatives. You can't square root negatives. You can't square root negatives. And then your Algebra 2 teacher last semester, hopefully, came along and said, well, what if we actually do want to square root negatives? And we told you about this number that we invented that allows us to square root negatives. We said, let's call the square root of negative 1 I. Let's invent this new number. They actually invented a new number at some point in math history called I. What actually happened was, you guys know there's the quadratic formula that allows you to solve any quadratic equation with x squared in it. Well, someone was trying to work on something to solve any cubic equation. Any equation that has x cubed as the highest degree, the highest exponent. They were trying to work out a process to solve any kind of equation like that, like a cubic formula except quadratic. And it turned out that even if the equation had real number solutions, sometimes they had to work with square roots of negatives to be able to do it. So they said, well, let's come up with this way to do it. Let's come up with something called I that allows us to square root negatives. And then they were able to solve any cubic equation, making use of that. Right? So we've got I here. It's called an imaginary number. It's kind of a silly term, right? It's not just in your imagination. It is a real thing that's used to solve real problems that has real number solutions. So we've got this I here, and so of course if the square root of negative 1 is I, then that means if we square it, then it gives us negative 1. And of course that's why we had to invent that new number there. Normally if you square something, you're going to get a positive number. For real numbers, positive times positive is positive. Negative times negative is positive. So we had to invent a new kind of number that we could multiply by itself and get a negative number. Right, so that's imaginary numbers. Then we also have complex numbers where we put real and imaginary numbers together. Something that looks like a plus bi. So it can have a real number part. A can be a real number, and then it has an imaginary part, the bi part, where that I makes it an imaginary number. And so real numbers are complex numbers. If you make b be 0, if b is 0, then you'll have a real number. Imaginary numbers are complex numbers. If you make a be 0, if a is 0, then you get an imaginary number. And then you can have any kind of combination you want for a complex number. And the math of them is fairly simple. If you want to add complex numbers, you add the real parts together. 6 and 4 is 10. And you add the imaginary number or the imaginary parts together, 5i minus 7i, just like if it was 5x minus 7x. Then you get minus 2i, and that's it. Just kind of like combining like terms. You combine the real parts together and combine the imaginary parts together. Then to multiply them together, you just pretend like the I is x at first. Just multiply that out, whether you use FOIL or a double rainbow or a box, whatever you like to do. Multiply that together, you'll get 5. You'll have 20i minus 2i. 20i is minus 2i's. You've got 18i's. And then the thing to be really careful about is you start to get some negatives flying around. So we'll be careful here. So we're going to have minus 8, and then it's going to be I squared. Right? I find that people that don't write the I squared first and then deal with that in a separate step tend to make mistakes pretty frequently on this. So I like to write the I squared first and then deal with it. Do make sure you realize you actually have to deal with it, though. That's the other thing. Some people just stop there. Remember, I is a number. We're treating it kind of like x so far, but I is a number. So we're going to replace that with negative 1. So 5 plus 18i minus 8 times negative 1. So 5 plus 18i plus 8. So the I squared is going to change the sign of that right there. Then we've got some like terms to combine, the 5 and the 8. So we get 13 plus 18i. All right, hopefully this is a review from last term or from whatever you took Algebra 2 honors for you. But why don't you take just a minute and try part C and D. Make sure you remember these complex numbers. And so there's the answers there. On part C, you would just have to make sure that you distribute that negative over to the right side there. And then For part D, again, just be careful with that I squared. All right, so now what we're going to look at is how these complex numbers can come into play with polynomials when we're trying to find the zeros or solutions for polynomials. Okay, so let's say that we want to solve x squared plus 25 is 0. So we'd subtract the 25 over. X squared equals negative 25. And so then we would square root both sides. And before, we would have just stopped. We would have said, well, I can't square root a negative, so no solution, and be done with it. And so we could say no real solutions here. If you were only asked for real number solutions, then you would say no solution. But if we wanted any possible solutions in all the world, we could do this here. We'd have to make sure that we remember when we say x equals here, if we added square roots, when we add square roots to both sides of the problem, we add plus or minus. And then, so we've got the square root of negative 25 here. So we know that square root of negative 1 is I. So how do we make use of that? Well, negative 25 is negative 1 times 25. So we've got a square root of negative 1 mixed in here. So we can say this is plus or minus. We'll have square root of 25 times square root of negative 1. So times I. And so what we get is plus or minus 5i. So that's our solution there, imaginary number solution. Can only do this if we're looking for complex number solutions, not just real number solutions. Okay. So then take a look at problem B right here. Unfortunately, it doesn't factor. Don't just give up. Sometimes I have students that are just like, oh, it doesn't factor. I'm done. I can't do it. No, no. Hopefully, you're more advanced in your mathematical algebraic skills than that. Hopefully, remember there are a couple options for solving quadratics that don't factor. Completing the square, we usually only want to do if like the middle number is even, and probably only if the the leading coefficient is just 1 right there. So a nice simple one like this, we can use completing the square. If it was more complicated, if it had if A wasn't 1, if B was an odd number, it's usually a lot easier to just do the quadratic formula. But this one, either one, whichever one you prefer. What completing the square was first we got rid of this constant right here, the 10. We moved that over to the other side. So we said x squared minus 2x, and then leave a blank right there. We've got that negative 10. And completing the square means we're going to try to make this look like something squared. And so what I like to do is I like to fill this in first. I think, okay, what is this going to have to be? X, well, it's going to have to be a minus. And then what number could go here that would give me 2x? X minus the number times x minus that same number. When I multiply it out, I would have 2x. Well, that has to be x minus 1. X minus 1 times x minus 1. I would have x squared. I'd have minus 1x would give me the minus 2x. But then there'd be something else, wouldn't there? There'd be a final term. There'd be a constant. If I multiplied this all out, I would have plus 1 at the end, right? Well, that means that back here, I have to have this plus 1. Well, whatever I do to one side, I've got to do to the other. Okay. If the way I just explained it didn't make as much sense, the rule for finding that number is you take half of b and you square it. So half of negative 2 is negative 1. Negative 1 times negative 1 is positive 1. Half of b and square it. And that's what you have to add to both sides. And so negative 10 plus 1, that's negative 9 right there. And then the reason why we do this, the reason why we wanted to write it as something squared, is that then I can square root both sides. Make sure when you add square roots to both sides, you add the plus or minus. And so we've got x minus 1 equals, and again, square root of a negative means we're going to have I, and then square root of 9 is 3. And so then we're going to add the 1 over there, but when I add 1, I can't actually add 1 to this right here. They're not like terms, so I have to just write 1 plus or minus 3i when I add that 1 over. And so that is my answer. I can also do the quadratic formula if I don't like completing the square, or if this problem were a little bit uglier, then I wouldn't want to do completing the square. So We've got quadratic formula x equals the opposite of b. So since it's not negative b, it's the opposite of b, right? Since b is already negative, opposite of the negative is positive. Plus or minus the square root b squared is 4. Minus 4 times AC, 1 times 10 is 10. All over 2a, so all over 2. So 2 plus or minus the square root of negative 36, all over 2. 2 plus or minus 6i, all over 2. And then make sure you realize you've got that distributive property of division, right? That's 2 over 2 plus or minus 6i over 2. Both of them have to be divided by the 2. And so 1 plus or minus 3i. Same answer, because math works. All right, so now let's get back into those higher degree polynomials that we've been looking at this chapter. This was kind of some review of complex numbers and quadratics there. Let's kind of step back up to pre-cal level here. Let's look at these higher level polynomials where we want to find all zeros. So what we were doing in the previous section, well, as we said, well, there's really nothing that we can see here right now. We can't do factoring by grouping. There's no way for us to do this by hand right now without just a lot of guesswork, and we don't want guesswork. So let's use technology. Let's be happy that we're in the 21st century. We started out with our calculator. 2x to the 5th plus 2x cubed plus 4x squared minus 24x plus 16, zoom 6. All right, so what we've got is a couple zeros that we can see right here. That looks like -2. I can double check it with trace. You could do calc 0 if you want, but if you're pretty sure you know what the answer is, just use trace to double check. All right, and then over here, that's 1. So I can trace 1, confirm it. Yep. Again, do at least trace though. You never know. It could be like 0.95 or something like that. So do either trace or calc 0 to check if that actually is the answer. All right. So we've got a couple answers from our calculator. Our calculator told us x equals -2 and 1. And then did you notice anything special about 1? Looks like it's a double root, right? It looks like it just barely touches. So 1 is probably a double root. So that counts doubly. So it looks like we've got 3 zeros right now. And well, all those were nice, right? So in the previous section, we talked about finding like exact values of the zeros, where we would do synthetic division to be able to solve to find if it was some ugly decimal, find the exact value of the decimal. These right now are all good. So you might be thinking, hey, I'm done. The calculator gave me everything. Except notice how we underlined and italicized all. Right? We don't just want real zeros anymore. So the ones that you're going to see in your calculator on the graph are only going to be real numbers. In graphs, everything is all real numbers. When we talk about x-intercepts, when we talk about asymptotes, anything that is related to a graph is only real numbers. So you're only seeing real numbers right here. But if I want all zeros, what if there are some complex number zeros? And in fact, there have to be. Right? There's something called the fundamental theorem of algebra that says if we're looking at complex numbers too, the degree is going to be equal to the number of zeros. Before we said the degree was the maximum number of zeros. Like if you've got x squared, well, you might have 2 zeros, you might have 1, you might have none. But now if we think about complex numbers, if it's x to the 5th, we have to have 5 zeros. This x to the 5th right here tells me there must be 5 zeros. So I've only found 3 of them so far. Again, the 1 does count twice because it's double root. But there must be a couple more complex zeros. So what I have to do is I have to do synthetic division and find those complex zeros. Right? So let's start with -2 here. Now, there's one little thing when I'm writing this out here. Okay, I've got 2, and then it goes from x to the 5th to x cubed. So what I need is a 0 term in there, right? I have to have plus 0x to the 4th. When you're doing synthetic division, if you're missing a term, then you have to have a 0 for that term. So I can't just go 2 and then 2. I've got to say it went from x to the 5th to x cubed. It's got to be a 0 for the x to the 4th term there. So 2 and then 0, and then 2 for negative 24 and 16. And then we do synthetic division. And bring down the 2, multiply, add them, multiply, add them, multiply. Remember, we're multiplying by the number in the box there. Add them, multiply, add them, multiply, and add. All right. And I went a little bit faster on that one because there's a nice check right here, right? I know whether or not I did this right. If that was a 0, then I have to have a 0 remainder. Right? So if I don't get a 0 remainder, then I went a little too fast. I go back and I double check. But I know I got that division right. Okay, now we can divide by the 1. We can just put the 1 in the box right next to this and keep dividing. Draw this line here, copy it down, multiply, add, multiply, add, multiply, add, multiply, and add. And again, we check and make sure that we've got that 0 remainder. All right, so now we've got a choice. There's actually 2 options right here. So we've divided by both the zeros that we have. So if we want, we could go ahead and write that out over there. And there is going to be a way to deal with that. Or we've got another option. Because it's a double root, we can actually divide again. If it's a double root, you're actually allowed to divide by it 2 times. You can double divide because it's a double root. So I can just put that 1 there again and just keep dividing. So I can bring down the 2, multiply, and add, multiply, and add, multiply, and add. And I get that 0 remainder. That tells me for sure that it actually is a double root, right? Because normally, if we just saw something like this, you might not want to be 100% convinced at that point it's a double root. We had some problems in the chapter P, right, where we had to do like a zoom box to really kind of focus in on that, and sometimes it actually did cross through and had 2 different solutions right there. So normally that's what I would have done. I didn't do that though because I knew I would be finding out later on for sure whether or not it was a double root. If I didn't get a 0 right here when I divided again, then I'd say, oh, that actually wasn't a double root, and I would have to look at it more carefully. Okay, so that's one option. You can divide again. So let me write this out right here. So one option is we divide again because it's a double root. That's option 1. Option 2 is, let's say you didn't think about that. Let's say that you had stopped right here. You divided by -2, you divided by 1, 1 division for each root. You've got each 0, you divide by 1 time, and that sounds right to you. So then you're right here, and you write this out. Remember, start from the right here. We've got constant x squared, x cubed. So this is, so here's option 2 here. We've got 2x cubed minus 2x squared plus 8x minus 8. And let's see if we can solve that now. Normally, we like to divide until we get down to a quadratic because we know we can solve a quadratic. But let's see if we might be able to solve this cubic here. We actually can solve that one. You see what you could do? This one could be factored by grouping. So I can factor out a 2x squared there, have x minus 1 here, factor out an 8 over there, and have an x minus 1 there. All right, because it's an even number of terms, and I get the same thing left right here when I factor it out from both parts. I can do grouping. So now I can factor out the x minus 1, and I've got that 2x squared plus 8 left. Okay? So notice either way, you're going to be getting 2x squared plus 8. Right? Down here, this is constant 8, 0 x's, and then 2x squared right there. Either way, I get 2x squared plus 8. This right here is also showing me that this is a double root. I already divided by x equals 1, and I'm getting x equals 1 again. This x minus 1 right here would go with x equals 1. So I got the x equals 1 once with dividing, and now I'm getting it again from my answer, so it was a double root. So I just need to figure out what are my answers from this 2x squared plus 8 part right here. So 2x squared plus 8 equals 0. So subtract the 8, divide by the 2, you're going to get x squared equals negative 4. And so then square root both sides there, and you'll get x equals plus or minus 2i. All right, now here's the annoying thing that's going to happen to some people. They're gonna do all this work to get down to plus or minus 2i, and they're gonna put that as their answer, and they're gonna lose some points. Right? That's not all the answers to the problem, right? How many answers were there supposed to be? There's supposed to be 5 zeros, 5 answers. Don't forget the easy ones from your calculator. Okay. We also had x equals negative 2 and 1. Put all those together, and that's your answer. Right? So, but that plus or minus 2i, that's what we had to do some work for. We couldn't see them on the graph. All we could see on the graph was the real numbers. These technically 3. It looks like 2 different zeros, but it's 3. The double root counts twice. We could only see the 3 real number ones. We had to synthetically divide to find the complex number ones. Okay, so why don't you go ahead and try numbers 4 and 5 here. All right, so on number 4, you need to find me 4 zeros. If there's a double root, that could count twice, but you need to find 4 zeros for me on number 4. And some of them might not show up on your graph. Those are going to be the imaginary number or complex 0 ones. And then number 5, you need to find me 3 zeros. So again, the game that we're playing here is we start in our calculator, find some nice zeros in our calculator, synthetically divide as much as you can, and then what's left should be something that you can solve by hand pretty easily. So go ahead and give that a try on number 4 and number 5. So we can check our answers here. On number 4, we had a double root again. Negative 1 was a double root. So you had those two choices again. You could either divide by negative 1 twice, or you could divide by negative 1 once, and then you could take this answer that you got right here, write it out, and do factoring by grouping. Either one. Either divide twice or just divide once and do factoring by grouping. Then we get that x squared plus 9 right there. We get that plus or minus 3i. Look what I did. I did that thing that I said was going to mess a lot of people up. I forgot to write all the answers together, right? So the answer right here actually should be and x equals negative 1. We'll just kind of make a box like that right there. Got to have all 3 answers. And really it counts as 4, right? Negative 1 is a double root. So x to the 4th, we need 4 zeros. 2 of them are the negative 1, and then plus or minus 3i is 2 more of them. Okay. On number 5, you get x equals 1 as your nice 0 from your calculator. And you synthetically divide that out, and you get this quadratic that doesn't factor. It's not nice and simple like the other ones. Hopefully you were able to do either completing the square or the quadratic formula on that one to figure out those zeros. And again, we do need to actually say all of the answers here. So it's not just 2 plus or minus 3i, it's also and x equals 1. That's the worst way to lose points on the test there. When you just type the answers that you just got at the end, you forget to actually type the easy one that you got from your calculator.